another problem, but I want to make sure I got it.
Sure,
right.
sure, I totally get it.
All right, folks. First of all, got some markers. Boy, I hope this will do. So, cost. Cost is just basic. C of X, they'll give it to you. How do you find average cost? C of X, plug it in.
C of X all over X. That'll tell you the average cost. It would also tell you average revenue, average profit. You just take the function and put it over X, and it makes it the average of that. Then what about marginal cost? That's really just the derivative of cost. And likewise, marginal profit, marginal revenue, it just means derivative of. Revenue, important formula would be that that is really what times what?
Price times.
Yeah, price times quantity. And the price they might give to you in the form of a demand function. D of Q is the demand function, which tells you the price. I see that. And then finally, profit is what? Profit is equal to
Cost minus.
Revenue minus.
Revenue minus.
yeah, revenue minus cost. All right, folks. So these are all of our main ideas. And then down at the bottom, I also said, how do you find the following? So how would you find a coordinate? How's it going, Alexis? You okay? You with us? All right. How do you find the coordinates? You know, if you know the x value, how do you find the y value? You just plug it into the function. Exactly right. And then how do you find a max or a min? Take the derivative and set it equal to 0. And how do you find inflection points? Take the second derivative and set it equal to 0. Thank you, Sheila. All right, so folks, we were, let's see here, today's October 15th. We're reviewing for your test, which is on Wednesday. And we were just finishing up section 2.10. So let's take out your section 2.10 and let's look at number 4 together. I'll tell you my joke. I think this is a pretty cute joke. Definitely something you can tell your friends. Why does Waldo wear stripes? You all know Waldo. Where's Waldo? It's that children's book. Where's Waldo? So why does Waldo wear stripes? Because he doesn't want to be spotted. Double entendre. Wordplay. All right. So number 4 says, given the demand function, and remember this demand function is not the price demand function we learned before. This demand function takes the input of price, and it tells you the output of quantity. So this demand function is actually telling us a quantity. This is interesting. It's saying, if you tell me how much you want to charge for your item, like a pizza, like you say, I want to charge $15 for my pizzas, this function is going to tell you how many people will actually show up and buy your pizza. Right? That's what this does. Or let's say you say, I want to sell this car for $1,000. Okay, that's not realistic. $10,000, still not realistic. $20,000. I want to sell my cars for $20,000. This formula would tell you how many people will show up to buy those cars. Okay, so that's the demand function, and they're saying find the elasticity. So our formula for elasticity is what? It's the absolute value of
P over the form, whatever the.
Yeah, P over the demand function of price times the first derivative. Okay, so that's the formula that we're trying to compute. So we already know P is just a variable. D of P is this formula right here. And so all we need to know real quick is the derivative. So the derivative is simply Savia, what's our derivative? Derivative of 200 is, oh yeah, negative 8p. There you go. Because the derivative of 200 is nothing, and the derivative of negative 4p squared is just negative 8p. So there's our derivative. So now we plug all of that in, and we have p over 200 minus 4p squared times negative 8p. And you might as well write negative 8p as a fraction over 1. All right, because that way the negative 8p is up in the numerator where it's supposed to be. And now we can multiply straight across, and we have the absolute value of negative 8p squared all over 200 minus 4p squared. That's our expression for elasticity. Now, by the way, folks, this is a class in advanced techniques for algebraic manipulation and simplification. I know that everyone has memorized that absolute value just makes everything positive. Does that mean that I can just go ahead and change that to a plus and change that to a plus?
No.
Definitely not. That would give us the wrong answer. We're still looking for a difference here. And we have to compute the whole thing. And when we're done, if it happens to be a negative number, we make it positive. But in the formula itself, we have to keep all those negative signs. So what did they ask us to do? Find the elasticity when you plug in 7. So I'm going to write E as a function. So I'm writing E of 7. That means I'm plugging in 7. So that means I have the absolute value of 7 squared 49 times 8, which is like 393? No, 392? All over 200 minus 4p squared. So again, 7 squared 49 times 4 is like 196. That's 4, which is whatever that is. Did I do any of those computations correct?
Yeah.
Are you folks checking?
I am.
Okay, thank you, Steve. 392 divided by 4 is absolute value of negative 98, which is 98. Now 98, that is a gigantically high value for E. Remember, elasticity is on a spectrum, which ideally we're looking at values between 0 and 1. Anything greater than 1 is called elastic, meaning demand is elastic, meaning people will refuse to buy your good because it's a luxury item and they don't want to pay that much. Whereas if the elasticity is between 0 and 1, it's inelastic, meaning that your good is a, what would you call that? Something that's not a luxury.
One.
Like you need it. You gotta buy it anyway. Like gas and plumbing and electricity. Like, what is that good? What is that called? It's not a luxury, it's a
Need.
A need, yeah, these are needs. That's better. Is luxury with 2 U's? Luxury? Is it luxury with 2 U's?
Yeah.
Wow, okay. All right, so we computed a value of 98. That's way over here. So that means people are definitely choosing not to buy your good because they're like, yo, $7, way too expensive. I'm not gonna buy that. What could you imagine is way too expensive at $7? You would never buy it. A what?
Beef jerky.
A single piece of beef jerky?
No, the packet of beef.
A whole packet of beef jerky?
At work, we sell beef jerky for $7.
You do?
Yeah.
What work?
At their
Oh, the airport. I was about to say movie theaters, airports. That's totally how much they're going to charge for beef jerky. But yeah, like if you were at a grocery store, $7 for beef jerky, you're probably like, you know what, I'm not going to get the beef jerky. A stick of gum. If it was $7 for a stick of gum, probably not going to buy it. Yeah, you're like, no, forget it. Okay, so at this price, we would say the demand is very elastic, meaning people are saying no. And based on this, you should definitely lower prices. And remember, that's what your whole spectrum means. So here you would raise prices. Here you would lower prices. Now, at the end of the last class, we agreed that what you really want for your product is when you compute elasticity, what do you want it to equal?
0. Right.
Not 0.
1.
1. Because 1 means you have the sweet spot. You have exactly computed the right price. You shouldn't raise the price. You shouldn't lower the price. You're charging exactly how much the market says you should charge. So if we wanted to, we could take our formula now. Let's try this again. And I can say I want negative 8p squared over 200 minus 4p squared. I want that to equal 1, or I want that to equal negative 1. Because either way, whatever that thing equals inside the absolute value, that has to either equal 1 or negative 1, and that would be the right price. So now I can go ahead and solve either of these equations. Negative 8p squared equals 200 minus 4p squared, which is negative 4p squared, which is p squared equals, goodness, negative 50? That's not going to work out very well. So p is 7.1i. Guessing that's not a good solution because we square rooted a negative. So that's right out. So we should not charge an imaginary $7.1. On the other hand, if we go ahead and solve this, we'd have negative 8p squared equals negative 200 plus 4p squared. Bringing the 4p squared over, minus 12p squared equals negative 200. And so p squared equals whatever that is, 200 divided by 12, which is 16.6, repeating. And then you square both sides and you get p should be $4.08. Plus or minus, but the minus solution obviously doesn't count. You shouldn't charge negative $4. It should be $4. So, in theory, What would happen if I plug 4.08 into this formula? What elasticity will I get? There goes right. What elasticity will I compute if I plug in $4.08? 1. It should equal 1. Right? I mean, in theory, that's what we just did. We just set that formula equal to 1. So let's just try -8 times 4.08 squared, and then divided by 200 minus 4.08 squared. Yeah, it technically equaled -0.9999999. But if I plug this in, elasticity is -0.99999 inside the absolute value, which is 0.999, which is awfully close to 1. Which means you don't have to raise the price or lower the price. $4.08 is how much you should be charging for that turkey. Yeah, Stephen?
So, question, how come you equaled it to 1, -1?
Because
just out of curiosity.
we want elasticity to equal 1, right?
Yes.
And the formula for elasticity is inside an absolute value symbol. So whatever is inside that absolute value symbol, what do I want it to be?
1.
Or
Or -1.
exactly.
Okay, that makes sense.
Yeah, good question. All right, well, that was number 4, folks. So I think there's just one more. You can all skip 5 and cross it out. And 6 you can cross out. It's just like one we already did. And now 7. 7 is a genuinely new problem. We haven't done one like 7 yet. And so same question. A business owner could use this model of elasticity to figure out how much they should charge for their product. Allison, you sure can. That is provided I have another calculator. Which so far I don't see. Right? No, 210, right? Golly gee, I don't see it. I don't have another copy. But for now, you can easily put this on a sheet of line paper and just start writing. Okay, folks, last question to try. So elasticity, again, the formula is P over D of P times the derivative of D of P. And so our derivative is very easy to compute. The derivative is just -2. So we plug all of that in. We have P over -2P plus 153 times -2 over 1, which is -2P over -2P plus 153. Now that's just our formula for elasticity. And so now we plug in 38. So they're saying calculate the elasticity at 38. Is that too high? Is that too low? So in your calculator, you would plug in 38. And that would give us -2 times 38 divided by -2 times 38 plus 153. I got an absolute value of -0.987. Hey, that's great. That's really close to 1. What does that tell us we should do with our price? We're currently charging $38. Should we keep it the same, raise it, or lower it?
Raise it.
You can raise it a little bit, just a teeny little bit. You could raise that price and people would still buy your product. So again, think about your elasticity spectrum. You're going from 0 to 1. In here is inelastic. Over here is elastic. Here you should raise your prices, and here you should lower your prices. And so with a value of 0.98, we can raise our price ever so slightly. Now, what does that even mean? Raise it ever so slightly. Isn't that very subjective? How much should I raise $38 to? I mean, maybe to you, raising it a little would be $38 and a penny. You know, theoretically, that's not going to stop anybody from buying your product. But maybe to you, raising it a little means raising it all the way up to 45. You're like, hey, somebody who can afford 38 bucks, surely they can afford 45. So how do we actually find out how much you should raise it by? How much should you raise it by? A penny? $5? $10? What do we do? What do we want elasticity to equal? 1. 1. So we take this expression and we say, I either want that to equal 1, or I want that to equal -1. And you would just have to solve that. And that's going to tell you how much is too much. So that would be -2p equals -2p plus 153. Ooh, notice something interesting happens here. We end up with 0 equals 153. This equation doesn't even have a solution. So this elasticity will never equal 1. But it could equal, sorry, -1. So now -2p equals 2p minus 153. And we bring the 2p over, and we get -4p equals -153. And so p equals whatever 153 divided by 4 is, which is 38.25. Oh boy, was that a surprise ending or what? How much could you raise the price by? A quarter. You could raise the price by 25 cents and you're not going to lose any of your customers. All those people that were willing to spend $38 were still willing to spend $38.25. What would happen if you raised the price to $38.26? At least one of the people who was about to buy your product is like, no, I've had enough. I'm not going to buy your crummy product anymore. I would have spent $38.25, but not $38.26. I draw the line. Can you imagine not buying a product over a penny? Probably not. I mean, this is a theoretical model. There's probably not any actual human who would draw the line over a penny. And what if you showed up at a store and you only had $38.25, but it was $38.26? Do you think they would just give you the penny? Mm-hmm. Would the cashier just be like, don't worry, I've got an extra penny right here? You do give somebody a penny?
When other people and other customers get their change, they give it to somebody else, then we put it on the side and give it to somebody else with any change.
That's very nice of you. Is there anybody who just takes that money every time? Oh, okay.
Sometimes I forget.
Yeah. All right. Well, there we go, folks. So this is an interesting, very interesting tool that allows you to know how much to charge to make the most revenue. Keep in mind, though, how on earth do you find this demand function, right? All this, using this whole tool rests on the idea that you have God's knowledge of the demand function of your market, of how much you can charge for your product and how many people will buy it. Okay, well, folks, I think that's it. That's section 210. So that brings us up to the practices. Yes, Bata?
What could be 38.01?
That was just a wild guess. I was asking everybody, since $38 is how much we did charge, but the elasticity says we could raise the price. I was asking, how much can you raise the price by? Can you raise it by a penny? Can you raise it by $7? Like, how much can you raise it by and not lose anybody?
Okay, so whatever the difference we got in the final answer, that is the amount that we should have.
That's the theoretical value you should charge, which is the maximum you can charge and still get all the same number of customers you were getting when you charged 38. Yeah. Okay. Well, folks, here's what we're going to do next. We're going to look at our practice test. And how many questions are on the practice test? I believe I have it all written in order. It goes up to 40. Is that right?
I think you got rid of some questions.
Yeah, that's the old.
Oh, really?
Yeah, we only have 20.
Oh, okay, well, wonderful. So here's what we're going to do, folks. There's probably less than 20 of you. So I'm going to write up numbers 1 through 20 on the board, and everybody gets to choose one problem that you're going to present on the board. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, 12, 13, 14, 15, 16, 17, 19, 20. So everybody come on up. First come, first serve. Choose one problem that you'd like to present.
Actually, reviewing some hard ones up there.
Can I call dibs at the lowest bottom of the board?
So you can reach, Alexis? Is that why?
Can't reach the piano. Just check it right there.
Just a big line.
Piano.
Hey, sure enough, there's only 20 questions. Now, see, wasn't that kind of me? I reduced the practice test from 40 to 20. Yeah, a little bit. Yeah, because I had some duplicate questions, like asking you to do the same kind of thing twice, and there's just no need for that.
Are we just writing it up there, or are we teaching them?
No, you just write it up. Because what I want to do is I want to have all the rest of this time to just walk around the room and interact with each person. So, folks, let me make a quick announcement. I'm just fixing my PowerPoint so I can put the problems up on the board. What we're going to do for the rest of class is I'm going to walk around the room and help each of you one-on-one. So whatever questions you have, I'll get to your desk and I'll say, what questions do you have? And you'll say, Mr. G, I'd like to look at number 3. And then we'll do number 3 together. And then I'll keep walking around the room. Meanwhile, up at the board, a few of you will be up at the board just writing the solution. We won't watch you, make you feel nervous or anything like that. You're just writing up your solution. And then once everybody at the board is done writing, I'll go up to the board and review those solutions, and then we'll start all over again. And the next batch of people will go up to the board, write up their solution while I'm walking around the room helping you, and then we'll just keep going like that for the rest of the hour. Now, when I get to your desk, I really hope you have a question. Like when I get to you and I say, hey, what question you want to go over? I hope you don't say, nothing. I really hope you do have a problem or two that you want to look at, because that's what makes this time valuable. If you want to ask a totally unrelated question, like about life or philosophy, you could do that, but I can't guarantee I have the answer. Also, during this time, folks, you're welcome to work with each other. So if you're sitting next to somebody, you can scoot even closer and go over the practice test together and say, hey, how did you get that one? So this is essentially a work session. I expect the room to be somewhat noisy, except for when I go up to the front to review the solution. Yeah. I do. Yeah, let me give it to you. Who just said that?
Me.
Who's me?
Allison.
Allison.
I said me.
Me listen.
How my life is going.
Do you have a game today, Allison?
Yeah, we have 4 this week.
Wow.
Yeah. This is the last week. Oh. Are you guys having well, it's supposed to be on Saturday. So
Okay, so, oh, well, hold on.
I know what
Okay, so folks, can I have your attention real quick? First of all, I'd just like to point out that the first practice test I passed out to some of you last week had 40 questions. Now the practice test only has 20 questions. So I hope that you all found that helpful. And Alexis, remember in the first test you said, hey, will you tell us what problems we don't have to study? I effectively took 20 questions off. That's pretty good, right? Okay, just wanted to make sure that that qualifies for your request to cut it down. Okay, so Like I said, there's a work session, so the first 3 people can come on up. So that would be Diego, Sila, and Cheryl. And I've got the 3 questions up here. Now, I don't think that all 3 of you should just stand right here and try to write the answers. You know, one of you can come over here, and then another person in the middle, and another person to the right. So use as much space as you like. And goodness, I only have 2 markers. So you'll have to take turns with the markers. There's one, there's one. Okay. So yeah, what's your question? Well, I'd really like to help you with the practice test. If I open the practice test, here's y'all. Okay, go for it. All right. What question? Okay, well, let's look at your work, because I think you probably got it relatively right. Are you doing this one? But it's this one. Okay, so first do the square roots. I'm sorry, not square root, the derivative. So it's 1/2 x one. Then 1/4 a 1/2. That's correct. And then you rewrite it as a fraction. Where did you put that? Like, where did you put this thing? So this is the derivative, which that's what this is. So you would have that over that times whatever this is. So already I think that's where it is. So looking at this, the 1/2, the 1 is in the numerator, the 2 is in the denominator. This whole thing to the -1/2 means this goes into the denominator, there's a square root. And then you also have a -4, which technically is -4 once, the -1 goes up. So, and there's a 1 up there. So that's what we have so far. -4 over 2, that's so that's what we have. So first we want to multiply that together to get a simple answer. So on the top we have -4p. And on the bottom you have 2. And then you also have this root times the same root. And if you multiply a root times itself, it takes away the root, and so you just have 200 minus 1. So now what do we have? Now we have -4p all over 400 minus 8. You agree? Okay, that's what the whole thing simplifies down to. So now you would plug in whatever it is you're supposed to plug in on 0.7. Does that help? Okay, try that again. Let me know how it goes. Is it deal? Okay, so first of all, your graph looks very nice. Now, is this what I had on my paper? Okay, so your question is, how do you actually do it? It says find the local min and the endpoints. So to find the local min, well, that's easy enough. You take the derivative and set it equal to 0. So the derivative of this is -4x. Because the derivative of 5 is nothing. The derivative of 2 is -4. Set it equal to 0, and therefore x equals 0. So that's where my local min is. If I want the actual coordinate, I plug 0 back into the function. And so my actual coordinate is that 0 squared is 0, 0 times 2 is 0, 5 minus 0 is 5. So my coordinate is 0, 5. That's where the local maximum min is. That's the flat spot. So there's a flat spot. And so far I'm just going to start a little graph to think about what's happening. So I have a flat spot at 0, 5. I don't know yet if that flat spot is a max or a min. I just know that it's a flat spot. So then what? Now I find the endpoints. So the endpoint, I'm only looking at the interval from -4 to 2. So I'm going over here to -4. I'm going over here to 2. So now, how do I find the endpoint? Again, anytime you want a coordinate, you just plug in the function. I plug 4 into that. -4 squared is 16. 2 times 16 is 32. 5 minus 32 is -27. So I have a coordinate at -4, -27. The other coordinate, I plug in 2. 2 squared is 4. 2 to 4 is 8. 5 minus 8 is -3. Another coordinate is 2, -3. Now if I just take a look at that on my y-axis, -427 is way down here. -4. 2, -3 is just down here. So now I have 3 points. And I know that it's a continuous function, so I can go ahead and just draw a line through them. Therefore, that flat spot must be a maximum. How's that sound? Okay, so now the questions. Oh, yeah. Yeah, this one was when you plugged in 0, you got 5, and that's the local minimum, because we took the derivative and set it equal to 0. You knew that it was a flat spot. And since my other 2 points are here, to connect them all together, I know that that's not, so I'm not that. That's it. That's all I wanted to know. So that's the local max. Yeah, just plug it in. Good question. Okay, folks, so far so good. I got to talk to a couple people and answer questions. Let's all together review questions 1, 2, and 3. Wait, did someone do? Yeah, number 1. Let's review number 1, 2, and 3. And yes, Allison? Oh, yeah. Oh, Allison, I just found 2.10. Lucky you, now you have 4. All right, folks, number 1, which was brought to you by Diego. So, folks, take a look at Diego's solution. It said just to use the chain rule to find the derivative. And remember, the chain rule states you take the derivative of the outside, leaving the inside alone, and then multiply by the derivative of the inside. And that's what he did. He did 18 times 2 is 36. He left the inside alone. He subtracted 1 from the exponent to get 17. And then he multiplied by the derivative of the inside, which is as he wrote it. So let's say that's the chain rule. Now, on the test, should I give you formulas?
Yeah.
I suppose I can give you formulas. So for instance, on the test, I would say the chain rule of the derivative of f of g of x, I would give you is the derivative of the outside, leave the inside alone, times the derivative of the inside. So sure, I feel perfectly fine giving you that formula. It's still up to you to remember how to verbalize that. Take the derivative of the outside, leaving the inside alone, multiply by the derivative of the inside. Okay, thank you, Diego. Number 2, by Sila. Number 2, use the chain rule again. So the chain rule, you take the derivative of the outside, leaving the inside alone, you multiply by the derivative of the inside. That's what Sila did. She took the derivative of the outside, so she multiplied by -3, subtracted 1, left the inside alone, and then what? Sila, did you just forget to write down times the derivative of the inside?
Oh, yeah.
I think so. Okay, so now she had the -3 times the 2, which was -6, leaving the inside alone all to the -4th. And she even rewrote it in a very nice user-friendly way. The negative exponent means to push that term to the denominator, which she did. We just want parentheses right there. You see that? You just want parentheses on the bottom to make sure they know the 4th power goes on the whole thing. And that's it. That's a really nice solution. So Sila and Diego, both of those solutions would get full points so far. And I realize that's not a ton of work, right? Like Diego's, he just wrote down the answer. There was no other work to show other than the answer. For Sila's, there was a little more work to show because she had to simplify, multiplying the 2 times the -3 to get -6, and then pushing that term to the denominator. I want to see that extra work of simplification because it makes the answer look good. Simone? Question? Okay. All right, thank you, Sila. Thank you, Diego. Number 3, Miss Cheryl. So Miss Cheryl was taking the derivative of this function, which again is the chain rule. She's got the inside and the outside function is the square root. So the outside was the square root, the inside was the 2x squared term. And so she rewrote it as, Miss Cheryl, I think what I'm going to do here is you have, the original function was something to the 1/2. So that's the original function. And then, Miss Cheryl, after that you took the derivative, right? So then this would be f prime of x, right? Just to be clear. So now, yes, you did it. You took the derivative of the outside, you brought the 1/2 down, and then subtracting 1, that should be a -1/2, right? And then she left the inside alone, but then she took the derivative and multiplied by the derivative, which was 4x plus 5. And all of that is correct. And so then you have to turn it into a fraction. So the 1/2, the 1 stays in the numerator, the 2 goes in the denominator. This whole term has a negative exponent, so it goes into the denominator as a square root. So I'm just going to throw that square root symbol over it. And then the 4x plus 5 stays in the numerator, which you have. And then you just distributed the 1, so you had 4x plus 5 all over 2 times that big root. And that's correct. Very nice. So on the actual test, will I give you 3 chain rule problems in a row? Maybe not 3, maybe just 2. Yeah, but definitely each of those is a great example of a chain rule of something you'd like to know how to do. Simone.
So can you just say it one more time? The chain rule is
The derivative of the outside, leave the inside alone, times the derivative of the inside. And did any of you ever see that movie? I'm forgetting the name. It was that calculus teacher back in like the 80s who taught a group of hardcore students calculus. It was Gosh, what is the name of that movie? Math movie about California teacher who taught. What is it? Stand and Deliver. There we go. Did anyone ever see Stand and Deliver? YouTube, Stand and Deliver. So a very inspirational movie. Is this it? No, that's way too long.
John killed himself. Harvey John.
How is that? Why did he do this? No sense.
How could he not leave a note? How could anyone?
Gosh.
The truth is that we don't.
Negative. Ah, there we go. Okay, so this is just a scene from this movie. Again, if you haven't seen Stand and Deliver, it's an inspirational, great movie. And so here he is. It's at the beginning of the school year, and he's about to teach all of them calculus. And these are high school kids. And they don't know that a negative times a negative is a positive. Right? So there's a long way to go to get to calculus. And so here he is on the very first day of school.
A negative times a negative equals a positive. Say it. A negative times a negative equals a positive. Say it. Negative times a negative equals a positive. Again. A negative times a negative equals a positive. A negative times a negative equals a positive. I can't hear you. A negative times a negative equals a positive. Louder. A negative times a negative equals a positive. Louder.
I know this is a very exciting scene. You're like on the edge of your seat, like what's going to happen next? Is a negative times a negative still a positive? And yeah, the answer is yes, it's still a positive. The point is, he knows what anybody knows is that in order to learn something, you have to repeat it over and over and over again. And more importantly, you have to say it out loud. So, Simone, thank you for asking to hear it again. It's so important to hear this over and over again, but even more important, it's important for you to say it over and over again. So like if I were you and I'm driving home today, I'd be saying it. Derivative of the outside, leave the inside alone, times the derivative of the inside. And just say it over and over and over again. Because you put that muscle memory in your tongue, in your mouth, and eventually you're going to memorize it. So thank you, Simone. Definitely want to say that over and over again. All right, I'm going to keep walking around the room. Let's go and have number 4, which is Cece. Is that you, Simone?
Now you know my name.
All right. So just Simone, actually. Well, no, let's have 4 and 5 come up. So number 4 and number 5. Wow, whoever signed up for number 5, that's a good long problem. Way to go, Efren. That's some courage there, Efren. Okay, so 4 and 5. Let's have 4 and 5 come up. Simone and Efren. And meanwhile, I'm just going to walk around the room and help you with your questions. All right. Sally. Okay, great question. So it says consider this function, which is x to the 5th. So we already know what x to the 5th looks like. It's a cubic function, so it's going to look something like that. 1, 2, 3, 4, 5. Yeah, it could look like something like that. Maybe not all the width exactly touch the x-axis. It could actually be something like I'll touch the x-axis. Okay, so we have something that looks like that. And it says it has a reflection. So every time concave down turns to concave up. That's the question. So for instance, here's concave down, and then here's concave up. So that means that I have an inflection point right. And then here's concave up, and here's concave down, so I have an inflection point right. And then that's concave down, and that's concave up, so I have an inflection point right. How many inflection points? So at most, I'm going to have 3 inflection points. So it has the inflection points D, E, and F, and they're saying from left to right. So I call that first inflection point D, the next inflection point E, the next inflection point. So find inflection points and put them on a number line from left to right. So you took your function, that one, you took the derivative once, you took the derivative again, and then you factor it out 60x. Yeah. And so that whole thing, remember you're taking the second derivative and setting it equal to 0. So you set that equal to 0, so you know that either this thing equals 0, in which case x equals 0, or this whole thing equals 0. Is that 4x squared plus 12x minus 10? And then you went and divided that by 2, so you had 2x squared plus 6x minus 5. And then you did the quadratic formula. Okay, so then one of your solutions is negative 3.7, and the other solution is 1. These are 5. Negative 3.68, 108, and 0. So on a number line, we would say, here's 0, that's one inflection point. 0.08, which is right over here. And then over here, negative 3.6. So we know that that's what our inflection points are. So that could mean that I'm going to change from concave down to concave up. And then I'll change from concave up to concave down. And then change from concave down. Something like that. So the graph could look something like that. Okay, but now it's saying, how do you know if it's concave down or up? Because I could have just drawn the whole graph backwards. Maybe I should have been going down. I'm sorry, concave up to concave down, concave up, down. So in order to figure that out, we choose test values. So anywhere. So just choose a value to the left of negative 3.6. It's easy. Negative what? It couldn't because negative 2 is in here. Yeah, well, we need something from over here, something from in here, something from in here, something from over here. Great. So try negative 4 over here. What's the number in between negative 3.6 and 0? You can do negative 2, you can do negative 1. You can do any value you like, just as long as it's in between these. Choose a value between these. Okay. Yeah. 0.5 isn't between 0 and 0.08. I think that's 8 cents. What's less than 8 cents?
I don't know which one it is.
No, okay, it's fine.
Yeah, 1 cent. So you could try 0.01.
No,
There we go. And then something bigger than 8 cents. So those are your 4 values that you're going to try. Okay? And then if you take those values and plug them into the second derivative, that's going to say it's concave up. Because if the second derivative is positive, it's concave up. If it's negative, it's concave up. So if you're going to take that whole prime, write down the list,
Yeah.
and write down f double prime, those values you can just say. So negative 4, negative 2, 1, and 1. Sorry, 0.41. And then when you plug those into your calculator, in the second derivative, keep in mind it has to be the second derivative that you're plugging it into. So you're going to be plugging it into this thing. Because you want concavity to work. So you plug it into the second derivative. So it's going to take a little time on your calculator. I would recommend if you're going to do this, I would type in this 240 something. I'm just going to put it something. So then I have to do 720 something.
I mean, I want to.
Then minus 600. Something. So that gives me the first answer. And then I just hit second enter and go back and change all those negative 4s into negative 2s. So then I go 2s. And then again, but right here, I should have parentheses there. So anyway, and then I go back through and I change all those negative 2s into 5s. To do that, you have to hit second insert.
Well, they're not like this.
Same thing, I did second insert, 101. That gives me the next answer. And then I finally want to change all those numbers. I want to change it to 1. I could not just change it to 9. But you just have to rewrite over and over there. So I'm changing Now, the key thing is, we just lost all that information, but we didn't. So the last one is positive 360. I don't even know right now. It's positive. The second answer was negative 5.9. The second answer before that was positive 2160. That's positive. The answer before that, watch as I hit second enter, when we go back through time. The first one, which is negative 4, that's that. There we go. So it's concave down. Inflection point, switch concave up, inflection point, switch concave down, inflection point. And now theoretically, if you were to graph that function, you should see it, which is exactly what I did. Now, does that answer your question? Yeah, I mean, you don't necessarily have to do anything with these. That's really just to say that from the interval, negative infinity to negative 3.68. So from within the interval, negative infinity to negative 3.68, you're saying, I'm choosing the value. Yeah, that's what you're saying. Okay, great, good question. Does it all make sense? Okay, try it out.
I could answer this.
Good question.
Great.
Question 7.
And it doesn't really help you to really go like into that.
Interesting. Oh, you know what? And that's because I didn't actually have
I can get my own
go all the way back up.
I go back to like other day.
And then just pull your right one, you just click here. And then go down to like level 2 and what section? You don't pay it back, but so go to 25B. So and before that got done, I got financially. Oh, it's in review mode, so it's not even showing. One of those problems I'm sure I did. But you got it. So that's great. And that was your only question so far, David? David? Question? How's life? Oh, you know pretty good. Good.
I know how it works now. I don't really well.
Is it teeny tiny? In fact, I just got one of the cutest pictures from my mom, who's watching him today. This was him, so we're there. What? Look at that. See you later. That's little Augustus. Yeah, over the summer. He was born July 21st. All right. What's that?
That's Mr.
July 21st? That's what? Oh. All right, folks. Let's take a look at the next question. So, who was next? That was Cece? Simone? Cece? So, Simone, is this it? These are your answers, right?
Yeah.
Okay, so let's look at Simone's work. First, she took her function and rewrote it into a manageable form using x to the negative 1 and x to the negative 2 so she could actually take the derivative. She took the first derivative by using the power rule, a 7 went away, and then that became, isn't that negative 4x to the negative 2?
Oh, yeah.
All right, and then negative 10x to negative 3, very nice, that's your first derivative. And then she went ahead and took the second derivative, so then that would become positive 8x to the negative 3 and positive 30x to the negative 4. And then, Simone, how would you write those in final form such that it's pleasing on the eye? Without negative exponents.
Oh, you want the fractions?
Yeah.
Isn't that 4x to, oh yeah, to the, yeah.
And then?
10 all over x to the number.
Yeah, very good. So that's what it would look like in final form, like what you would hand to someone, like a customer or a client. Likewise, this one you'd have 8 over x cubed plus 30 over x to the 4th. So just to be clear, this is perfectly fine, Simone, because this is how you were doing the derivative. But if you were actually giving your answer like to a client and they needed these formulas to do work, you would give it to them in this form. Because nobody likes a negative exponent. That could be a t-shirt. Nobody likes a negative exponent. You'd buy that t-shirt, right? That'd be funny? Okay. Well, thank you, Simone. So for the first derivative, what did you write down? Where's the rest of it? Wasn't the first derivative negative 4 over x squared minus 10 over x cubed? So did you mean negative 4 over x squared minus 10 over x cubed?
Yeah.
All right.
I'm sorry.
No, it's okay. I mean, you have the right information over there.
Yeah.
Okay, you're doing the problem right. And then what did you do? You just plugged in 2? Yeah. And folks, when you plug in 2, you can sit there and do the work by hand. Which is that. Or you can just plug it into your calculator. Either way, you get negative 2.25. And then, Simone, for your last one, what's the whole answer, Simone?
Yeah, so 8 all over x to the third plus 30. Oh, yes.
There you go. Why didn't you write the first part?
Oh, I'm sorry. I get nervous when I don't like everybody hearing me.
That's fine. You did great, Simone. You did great. So there's your answer, and then you plugged in 2, and again, you can just plug it into your calculator. And finally, f of 2, she plugged it into her calculator. There's one last thing to do, Simone. It says, draw a little sketch. Draw a little sketch. So folks, how do we draw a little sketch? At the point x equals 2. So you go over to the coordinate x equals 2, and you go in order of coordinate, first derivative, second derivative. So Simone, where's the coordinate? And everybody make sure you know how to interpret this. The coordinate is from the original function. So the coordinate is 2, 10.25. So Simone, there's your coordinate. Everybody, I am grading this on the test. What I really want to see is your little sketch. The little sketch is what's really most important. So that's the coordinate. And then Simone, first derivative, what's the slope? Positive, negative, or 0?
Down.
Yeah, exactly. It's negative. So I'm going to draw a little negative tangent line there. And then what's the slope? Concave up, concave down. Huh? Yeah, up. It's positive number, so it's concave up. And so I just make it a little bit like a smiley face there. And there's my little sketch. I don't know what's happening in the rest of the graph, but if I just zoomed in and looked right there, I would see something that looks like that.
And so everybody on your test, that's what I expect to see. I expect to see this little sketch of what's happening right there at 2. Okay, thank you, Simone. I know my phone just went off, but let's just finish this next problem by Efren. Efren is right over here, right? 5? Okay. Efren has said, consider the function 7x. Here, I'm going to write up the original. The original function was 7x plus 4 over x, which is really 7x plus 4x to the negative 1. And so it says, for this function, there are 4 important intervals where it's breaking up. If you just notice what this looks like, folks, they're going from negative infinity to point A, to point B, to point C, and then to positive infinity. And so the intervals are from negative infinity to A, from A to B, from B to C, and from C to infinity. Those are the 4 intervals that they're talking about. Where they say A and C are critical numbers, that means the first derivative is equal to 0, and the function is not defined at B, which means the first derivative is undefined. So we can even say here at A, the first derivative is equal to 0. At C, the first derivative is equal to 0. And at B, the first derivative is undefined. So does everyone see my picture here and see what we're shooting for? This is the big picture. That they're telling us that for this function, you've got 3 critical values where the first and last one are where the first derivative is equal to 0, and the middle one is where the first derivative is undefined. That's just the setup to understand the problem. So let's look at what Efren did. Efren took the first derivative, which became 7 minus 4 over x squared, which is what it would be because 7x plus 4x to the negative 1 becomes 7 minus 4x to the negative 2, which is as he said. So 7 minus 4 over x squared. He set 7 minus 4 over x squared equal to 0. And where was all your work for that, Efren?
Oh, I had all my paper.
Okay, well that's fine. So Efren had 7 minus 4 over x squared equal to 0. And he did show his work. Let's just real quick, you move the 4 over x squared to the other side. You cross multiply, 7x squared equals 4. You divide off to 7. You get 4 sevenths, and you square root both sides, and you get x equals plus or minus the square root of 4 sevenths. Which, oh, that's what he has right here. X equals plus or minus the square root of 4 sevenths, which is roughly 0.76. So going back to the original drawing, A is really negative 0.76. C is really positive 0.76. That's the first part of the process. Then he took the first derivative and said, when is it undefined? And when is this expression undefined? Just when x is 0, because you're not allowed to divide by 0. So now he knows that the other values when x is 0, and those are our values for A, B, and C. Okay, very nice, Efren. That totally all works. And then what? So the problem says find A, B, and C and draw a number line. There's our number line so far. We found A, B, and C. Now it says choose a test value between each critical point and determine if the function is increasing or decreasing. So what test values did you use, Efren?
I used negative 1.1 or negative 0.1.
Yeah, very good. That's perfect. He chose a value to the left of 0.76, would be which he used negative 1. And then he chose a value between negative 0.76 and 0, which is negative 0.1. And then he chose a value between 0 and 0.76, which he used 0.1. And then he chose a value greater than 0.76, and he used 1. So your test values were negative 1, negative 0.1, 0.1, and 1. And he plugged each of those into what? The what?
The original. Or the derivative.
Into the derivative, because we want to know if it's increasing or decreasing. And the derivative tells you if it's increasing or decreasing. So he plugged in all 4 of those values into the derivative, and he got the values plus 3, minus, and plus, which therefore means the function is increasing, decreasing, decreasing, and increasing. And by the way, if we actually looked at this graph to see what it looked like, it looks like this. So yes, indeed, it goes increasing, and then decreasing, and then still decreasing, and then increasing. So his prediction is correct. It went increase, decrease, decrease, increase, increase, decrease, decrease, increase. And keep in mind, when you're doing this problem on the test, and this problem is on the test, I'll just tell you. Not this exact problem, but a problem like it. You can always just graph it on your calculator, right? If you graphed it on your calculator, you could find the value 0.76 by just finding the max and the min. And you can just see that it's increasing, then decreasing, then decreasing, then increasing. So you can do a lot of this on your calculator. Okay, and finally, Efren had to figure out concavity. It says, note the function has no inflection points, but we can consider concavity to the left of b and to the right of b. That is, to the left of 0 and to the right of 0. So what value did you choose, Efren? To the left of 0.
For
The concavity part.
I just did 8.
8? No. Well, what did you plug in as a test value? -1 and +1?
-1, sorry.
Yeah, so choosing any value to the left of 0, any value to the right of 0, 1 is easiest. You plug that into the first derivative, the second derivative, and he got the answer -8 and +8. Negative means concave down, and positive means concave up. And again, you notice that that bears out in the graph. This part was concave down, and this part was concave up. So Efren, thank you very much for showing all of your work for this problem. You get full credit for all of this. I wouldn't mind seeing what test values you chose. I see the numbers that you actually got. I think that the one thing left that I would want to see on all of this is a number line. Because I did say, find ABC and draw a number line. So it wouldn't hurt. I do want to see this. Show me a number line with the -0.76, with the 0, and with the 0.76. And then show me what you're trying. Like try -1, try -0.1, try 0.1, and try 1. I'd like to see something like that, so I can better understand your chain of reasoning. Whew. All right, Efren, thank you very much. And thank you. Who did the previous one? Cece? Simone? Bata?
Number 4.
Yeah, and number 4?
How do we know the graph is concave out?
How do you know it's concave up? Because the second derivative came out to be a positive value.
The second derivative.
Yeah. Now remember that the second derivative tells you concavity, and if the answer is positive, it's concave up. If the answer is negative, it's concave down. Yeah. Okay, folks. We should go ahead and take a break. When we let's see, it's 11:59, so let's all come back at 12:09, and then we'll keep working. So everybody take a break if you like. Alexis. So profit was revenue minus cost, that minus that. Yeah. You got all that right. You took the derivative. That's so we're the divided by 0.6 on this. Well, that is the production line. In our function, whether we're looking at the function of cost, revenue, or profit, X is the quantity. It's the quantity of pizzas you're selling, the quantity of cars you're selling. And so you solve for X. And therefore, X represents quantity, which is how many of whatever it is. So the production level, that means how many you're selling. Production level is a phrase that means how many things should you produce. So like if you're a pizza company, how many pizzas are you going to sell? 2,166. Yeah. What's your production level? That is the answer. Yeah. Now when you type it into the program, it might want you to type in 2166.666, or it might just want 2167 because they want you to round. You might have to tweak your answer. Another question?
No, I just didn't know, like, if it was like another question.
Yeah.
Like, plug it in.
Nope. In this case, it just says find the production level, and therefore that's referring to the cost. If they actually said, now find the maximum profit.
We're trying to write it on boards.
You plug it in. The first one is cost. So I said find the maximum.
I don't know, I think Josh.
Yeah, you plug it in. Before you take the derivative. Yeah, the original profit. Yep. Good question. Where? That's what I got. And then if you actually plug that in, into this thing,
The function is not.
you wrote down the cost function.
So that's why it's defined.
We want to maximize profit. This is so.
So it's not defined, it is under.
So, yeah, this one is profit. The question says, for this, find the production level that will maximize profit. If you want maximum profit, over X, plug that value into profit. If you want maximum cost, you would plug that into that. You found the maximum cost. No, actually, you didn't find the maximum cost. You just found the cost associated with the maximum profit.
So the final answer.
But if you want the maximum profit,
If it was like, X, you know, it's 3 over, you know, 3 arguments, then it's not.
And it would be on X.
yeah, scientific notation, almost every calculator is gonna do that to you, it's very unfortunate.
So it's not always.
So what that means is, oh, you okay, this one first. 1.0 minus 85 times 10 to the 6, that's what that means. E to the 6. E6 means times 10 to the 6, which means we moved it out to 6 places to the right. So I move it 1, 2, 3, 4, 5, 6, so that's 1085. And then 1, 2, 3 additional zeros. So that's actually 1,085,000. Now, how do you get rid of the scientific notation? I have no idea how to do this calculation. Oh, very nice. Cool.
As soon as possible. Always begin with this.
And then you have 4 that
So it's still 12.
Oh,
So we just took 12 from this. So I probably took out the 10.
I already-
12 loops. So that's how it's. So that's just how it's. Why would you? 14 minutes.
I told her not to get that way. I told her I did not want it, and then I got it. I know, and I don't want it. I'm just there.
So. Very slowly, every time we sell something, whatever we got, we say we do it first. And then once we run out of that, we do the other. Okay. Yeah, so now we ended up selling all of this. And so we ignored the rest of it. We did what we can. Or just trying to.
That is actually number 4.6. Oh,
This is like,
Oh,
balancing from here to here.
Yeah, that's basically what it was and everything.
No one always has it, but if I get it, right.
And then the last first step.
So, last and first step.
So it's the same thing, only instead of selling the first and the second.
So, basically the same.
Basically the same thing. So we received more, we sold.
Yeah.
That's good. That's the first. So that's the card.
That makes sense, okay, good.
Yeah, so far.
I don't have your number, like,
Press on the tracker.
Oh, that's right. We did it on our.
Final everything.
What's ringing out?
Asked about chapter 6 notes. She just posted an email to her. Never posted about so said she posted chapter 6 notes.
I'm not even gonna do that.
But she didn't post it.
All the.
Are you going downstairs?
all the
Go to the bathroom.
videos and the-
Yeah, like you found videos now. Yeah, we didn't do it for chapter 6. So
Yes.
okay, I know, I did have check, so.
Hopefully.
No, you're good.
Okay, and so now your question is how to compute it?
Yeah, what I do is always.
No, dude, you're good. I was like, shoot, dude, I woke up like. I woke up like 11.
Oh yeah, no, about that. You don't have to do all that. You just type it in. So like right here, clear, so it'd be -0.3 parenthesis 2166.6 at squared.
I'm not using this Thursday.
Well, that's pi.
I think that was just the. What else we got?
There we go. So power 2. And then plus 1300 and then minus 6. Yeah, you type it in all at once.
Yeah, okay, so.
And then that's 1.40188 e to 6. So you can get the decimals.
Show me how that works.
No, you're good.
For that insurance statement.
Just like the closing statements.
Oh, yeah.
And so you don't know if
We do, we're both.
We have to study.
Probably.
Johnson might be on chapter 5. If it's going to be on, it's on
Yeah.
Oh, it's just sound good. Yeah.
Oh, yeah. I got a tea. James. I like
real.
Sir. Yeah. Wait, let me come to your desk because I'm gonna be there for this. All right, folks, let's keep going. We're on to number 6 and 7. Now 6 was Sadia and 7 no one signed up for, so I suppose I'll do number 7. Did everyone sign up? I guess so. I'll sign up for the rest that didn't get signed up for. That's only fair. So let's have Sadia and David come up. Let's have Sadia and David come up, and you can go ahead and do Sadia do 6 and David do 8. And if you just leave me the space right here at number 7, I'll do number 7. So Sadia and David, come on. Yes.
Can I do number 17 and 10?
Yeah. Oh yeah, absolutely. Sign up. Go up there and write your name. Okay, Steve.
So I have a question about how to type this in, because I typed it in my calculator, I got 3.70, but then on the answer key was 14.
Oh goodness, I'm a little concerned now. Let's see. Right, it's just reading. Yeah. Great.
Thank you.
Okay, so first of all, that's our function. So our first derivative.
This is first derivative right here. This is our second derivative right here.
Let me check your second derivative. 36. Yeah, okay, so that's our correct. So then you've solved that one because this down here is inflection points and concavity. So you had to find the inflection points, which were, those were the inflection points? Oh yeah, negative 12 plus or minus root 72. Okay, let's just check that. So 36 squared plus 24 x plus 2. 1 down. Oh, your buttons are so smooth and easy to push. I wonder if yours is. Okay, there we go. So now we just zoom in a little bit. All right, there. So it does look like your answers are correct. If I try them out, negative 0.5690. That's one of them. And if I try out the other one, negative 0.0976. That's the other one. Okay, those are the correct inflection points. And so on a number line, so here's one of them is a negative 0.56. And then the other one is negative 0.09. So we need to find values over here, here, and here. So this one I'm going to try negative 1. Here I'm going to try negative 0.1. And here I'm going to try 0. And you did negative 1, negative 1. Oh yeah, negative 0.5 works fine because it's still in between. That's fine. Let's just stick with that. And then there's 0. Okay. Now, hold on a second. We're looking at different problems.
Are we?
Yeah. That's why the answers are the same.
Oh, okay.
Yes, that's number 5.
So,
There we go. And I use negative 1, 0.5, negative 0.5, 0. Okay, well that's what you're about to try. And oh, okay, but the different values. So we have to plug it into the second derivative. And the second derivative, oh, I see. Okay, so my numbers are different. Yours still goes plus minus plus, and mine goes plus minus plus.
just different outcomes.
Yeah, and you know what I did? I didn't plug it into the e to the 6x. Because no matter what you plug in to e to the 6x, the answer is always positive.
Oh, okay.
And so all I did was compute the second part. So now I bet if we try that out. So 36 times negative 36 negative 1 squared plus 24 negative 1. Seriously, your calculator is so nice. Plus 2. That's the geekiest thing ever. You're like, man, I like the way this calculator feels. That's where I got the 14. I didn't multiply times e to that.
Okay.
That's not, that's not, I should have included it for the sake of everyone in here. But you see why I didn't?
Yes.
Because ultimately, the numbers don't even matter. All you really need is the plus or the
It's
minus.
like times it by 1 almost.
Yeah.
Okay. That definitely makes sense.
Okay, good question. Okay, folks, let's go ahead and move along here and try the next couple problems. Number 6 was done by Sadia. Thank you for Sadia. It said, here's the position of a particle. It's just a function. It says to find the velocity and then plug in 3. And so remember, in terms of derivatives, your first function, f of t, is position. And then your first derivative is velocity. And your second derivative is acceleration. So this problem is really simple. It's just asking you to take the first and second derivative and plug the numbers in. And that's what Sadia did. She took the first derivative, plugged in 3, second derivative, plugged in 3. So very nice. Thank you, Sadia. Number 7, I'll go ahead and do number 7. I'm not necessarily going to show all my work. Well, I mean, I could. So it says, consider this function. And we've looked at this function now a couple times. I hope you all have memorized what the graph looks like. It looks like that to the right, and then it goes up and back down to an asymptote on this side. So that's what all of these functions look like. X squared e to the something x. It looks like that. And it says f of x has 2 inflection points at C and D. So inflection points are when it changes from concave up to concave down. So if this is concave up and this is concave down, I have one inflection point right here. And then this is concave down, this is concave up. I have another inflection point right here. So I already know, roughly speaking, I have 2 inflection points that are negative values. So I'm going to call this one C, and I'm going to call that one D, because it says that C is less than D. Find both inflection points and label them on a number line. So my first derivative, the function is x squared e to the 6x. My first derivative, let's see, was e to the 6x times x, no. Is it 2x plus 6x squared? Was that the first derivative? Okay, great question. Okay, so let's look at how to do it. We have x squared times e to the 6x. Sela, thanks for asking. So folks, when you do the product rule, this is a product rule, I always write it out in parentheses first. Derivative of the first times the second plus derivative of the second times the first. So derivative of the first times the second plus the derivative of the second times the first. So how do you feel about that, Celia?
I got to that point.
Okay. I'm going to factor out e to the 6x. So I have e to the 6x out front of 2x plus 6x squared. So there's the first derivative. Did that answer your question, Celia? Because if you take out the e to the 6x, what you have left is just 2x plus 6x squared. All right, so that's the first derivative. Then you do the whole process over again to get the second derivative, where now you're saying the derivative of the first times the second plus derivative of the second times the first. So again, derivative of the first times the second plus derivative of the second times the first. Derivative of the first times the second plus the derivative of the second times the first. And then you factor out e to the 6x, and you're left with 12x plus 36x squared plus 2 plus 12x, which you then have to combine like terms. And what do we have? 36x squared plus 24x plus 2. All right, so that's our second derivative, e to the 6x times 36x squared plus 24x plus 2. Now, folks, even on a good day when you feel like you have tons of energy, just that you probably feel like is enough. Like, hey, that's a long problem in and of itself. But now we're asking to go a step further. We're saying, where are the inflection points? So when is this equal to 0? Because that's where our inflection points are going to be. So first of all, when is an exponential function equal to 0? Never. An exponential function is never equal to 0. So now we just have to know, when is this quadratic equal to 0? And to do that, you have to use the quadratic formula. You can factor out a 2 if you like, so that it's 18x squared plus 12x plus 1. But I don't think that factors. It does not. So you just have to use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac.
Will you put that on the test?
Yeah.
The quadratic one.
Oh, for sure. Yeah, you have to know the quadratic. Oh, you're saying you want me to put the formula? I can put the formula, sir.
Yeah.
Yeah. So b squared minus 4ac, that gives us 72 all over 2a, which is 36. And then that simplifies negative 12 plus or minus 6 root 2 all over 36. And that simplifies to negative 2 plus or minus root 2 all over 6. Now, whether you simplify all that or not, it doesn't matter. You can just stick with this and type it into your calculator and get 2 decimals. So I'm going to say negative 12 plus root 72 divided by 36. That's negative 0.097. And then negative 12 minus all that, and that's negative 0.569. So that answers the original question about the inflection points, negative 0.569 and negative 0.09. Okay, so that's all the work we've done so far. We found the second derivative. We set it equal to 0. You know that the exponential part is never going to equal 0, so you can just ignore that. Solve this part using the quadratic formula. Now we have our 2 decimals. Now what do? Yeah, test values. We look up test values. So you're just going to try a couple of values. Anything to the left of negative 0.56, I'm going to try negative 1. Anything in between there, I'm going to try negative 0.1. And then anything to the right of 0.097, I'm going to try 0. So there we go. Those are my 3 test values. It says to choose test values between each inflection point, determine if the following intervals are concave up or concave down. So what do we plug our test values into? The function, the first derivative, or the second derivative? The second derivative, because we want to know if it's concave up or down. So we would do f double prime of negative 1, f double prime of negative 0.1, and f double prime of 0. Now, folks, I was just talking with Stephen about this. If I plug negative 1 into this function, the second derivative, well, no matter what I plug into e to the 6x, that part is positive. Because e to the power of anything is going to be a positive number. So I already know that's positive. So all I really need to know is what happens when I plug negative 1 into this. And when I plug -1 into this, I get positive 14. And this is already positive, so a positive times a positive is still positive. I know that overall, this value is positive, which means concave up. When you do this part, you don't even have to do the actual computation. You don't need a number. You just need to know if it's positive or negative. And like I said, e to the 6x is always positive. So you're just wondering what's this. What's that?
So it doesn't affect when we compete on it or not.
Yeah, I mean, I don't need to see the actual decimal value there. It's really just, is it going to be positive or negative? So now when I plug in -0.1, this turned out to be what, Stephen?
I did 0.5.
Yeah, 0.5 something. Wait, it should be negative though, right?
Yeah, it's still negative.
Yeah, it turns out to be a negative number, and that means concave down. And then when I plug in 0 into this whole function, it turns out to be a positive number, which means concave up. And so if you look, it's concave up, concave down, concave up. So it goes up, down, up. And look at the graph. Concave up, concave down, concave up. And that's what you're expecting to see. Now, folks, number 7 is a really good problem. I'm pretty sure I put that on the test as well. So you want to practice that problem over and over until you can do it without, having to look back at your notes. This whole test value idea is really important, that you find inflection points and critical points by taking the derivative, setting it equal to 0. That just tells you the critical points. But then you try values in each interval to determine what the behavior of the graph is like. Okay. Simone, Cece.
What is that? What is this part called?
The product rule.
Okay. So just to find the second derivative, you need the product rule?
Yep. Yeah, well, to do both derivatives. You start with the function, you take the derivative once, that was the product rule. Take the derivative again, that's the product rule. Yeah. Now, folks, I hesitate to even show you this. But you know how every problem is it's x squared e to the something x? You did a homework problem where it's e to the 8x. You did a homework problem where it's like e to the 9x. You did different things. You could always do this whole process. It doesn't even matter to say. But you could solve the problem in general. So x squared e to the n x. When you do the first derivative, that's going to be e to the nx of 2x plus nx squared. And then when you do the second derivative, it's going to be n squared x squared plus 2nx. Wait, no, it's more than that. 4nx plus 2. So this is actually the general formula. Now, is that helpful to memorize the general formula? Like, because now I can just use that formula for, so whatever problem I give you on the test, let's say it's x squared e to the 8x, you can just plug in 8 for n. So just to notice that this formula works, if I plug in 6, that's e to the 6x times 36x squared plus 24x plus 2. Is that correct? Yeah, that's what we have. So would that be a valuable use of your time to memorize this formula? I don't know, maybe. I mean, it's a way you can check your work. But what am I looking for when I grade your test? I'm looking for the product rule. So Simone, I really do want to see you do the product rule and work it all the way out, doing the first derivative and then the second derivative. But if you wanted to, folks, you could write down the formula for the first derivative and the formula for the second derivative, and that way you could check your work and see if you got the right answer. But if you just use the formula, I won't give you full credit. I want to see the product rule. Simone, I don't know if that was your question, but it is important to show me the product rule. What?
Yes, is there any chance that this graph would be on the other side of the?
No.
So this is all the same?
Yeah. Yeah, no matter what value of n you choose, in this case it's 6, the graph is still going to look like this. The graph is always going to be a speed bump followed by a blast off. Yep. Yeah, and so you'll have a problem like that on the test.
And the product rule is the derivative of the first times the second plus the derivative of the second plus the first.
Exactly right. Way to go. Yeah, absolutely. So important you say it over and over again. Okay, number 8. Well, that was a nice short problem, number 8. Let's see here, David. You wrote down that at this point right here, the first derivative is negative because it's pointing down. And at this point right here, the concavity is positive since it's concave up. So that's it. Thank you, David. Well, you got it easy compared to some others, huh? All right, number 9. What do we have now? We have 9, which is Sarai, and then 10, which is me. So 9, 10, and let's have 11 come up. So how about Sarai and Bata? Come on up and do 9 and 11. Here's marker. All right. So let's see. I was just talking. Closer. Question. Okay. Well, let me know. Susie. Look at all this candy. Were you ever going to offer me anything? Oh, that's right. No, I'm kidding. Totally. Okay, Michelle. What's your question? No. Okay. Well, let me know. Did you get to check my email yet?
Oh, yeah.
Come on.
Okay.
Not yet.
Not yet.
Okay. Well, hold on before I leave. Before you leave. Steven.
Yes, okay, so I was kind of looking at this one so when these, I kind of lost my head, but we look at this and you go to graph, we want to find the derivative of it. But I think when it says draw a graph, I always have a hard time drawing those graphs.
Okay.
So,
Well,
4 equals like, we'll just have to.
Let me break it down for you. Yeah, thinking about a graph is really a table of values. So, for instance, in terms of x and f of x, I need some points to plot so I can draw it. One point I'm interested in is the critical point. And you already found the critical point. You took the derivative, set it equals 0, 0 is the critical point. The other 2 points I want are the endpoints. So that means plugging in a -4 and plugging in a 0.
Okay, I was going to ask. So even like that's going to be the case with all.
Yeah. So you go ahead and you plug in 0, so then that'd be 5. You plug in -4, that's -7. You plug in 2, and that's going to be -3. Right? So now those are all just coordinates. So if I go there, then 0, 5 is up here. -4, -27 is way down here. 2, -3 is like here. And since I know that that's the only critical point, it's either a max or a min. So it's either a max or a min. But the only way I can connect these 3 points into a graph is by graphing them like this. There's no other possibility. Like in calculus, we're guaranteed that if the point is here and here and here, it can't look like this. Because we already showed that there's only one critical point in the whole region. And if I graph it like that, I'd have 3 critical points. And that's not possible, because I already know there's only one critical point. So I know the graph has to look like this. And at that point, you're done. That's the graph.
Okay. And yeah, like that, I just have like drawing those graphs. So,
Yeah, but what you drew here is just fine, and it's just a matter of showing roughly speaking, like that's 5, that's -27, that's -3. You know, it's a real rough sketch.
okay.
That's that. You know, it doesn't have to be perfect. It just has to capture that information. Because do we know exactly how quickly this goes? No. I mean, the rest it could go out and then down, or maybe it comes, you know, almost directly down. We don't know the rest of that. It's just a rough sketch. All we know is that it goes that way and that way.
Okay. Then I can probably add a couple other questions. I'll look through.
Okay. Last, when you're making graphs, remember, whenever you have a table of values, people don't really write x, y, but it's really x, f of x, which implies that the y coordinate is f of x. So you're using your function over and over again to find coordinates.
Okay.
And the coordinates are what you plot and then graph.
Sounds good.
Okay.
Thank you.
Okay. Allison,
I do have a question.
I'm so glad.
I know you're about to go over it, but
That's fine.
when you plug these in, you plug them into the original or the derivative?
Allison, that is a fantastic question. Let's think of it. So we have this function, and it's x cubed. So we know that our function looks something like a single like that. Okay. So, and it says it has one local min and one local max. So the way I drew that, it looks correct. Oh no. I think I just. I'm not blaming you, I'm just sharing it. Oh no. Oh man, I know what piece of lead, that was like 2 pennies, right? There's probably a lot more than that. Gosh, these days. Actually, now I'm dying to know. Not gonna lose money. Really?
I never switch it out.
What? What do you mean you never switch it out?
Or mine,
Gosh, I have to buy new lead all the time.
or this.
I think oh my gosh. I realized I should just give up and answer the question. And I use it. Oh, I'm so sad right now. Okay. So our graph is going to look something like this. It says it has one local max. So that'd be like that one, and one local min. So what are the coordinates of the min? So you took your original function and you took the first derivative, and you know you're going to set that equals 0. You divide it by 6. You got that. You set it equals 0, and you know that the values are 7 and 1. So that means that on your graph, if you go 1 and 7, that's where you should have your max and your min. So now the question is just where is that max? How do you know this? So to find a coordinate, you plug those numbers into the original function. So yeah, you already answered your question. Plug it into the original. But to take your question one step further, if you plug it into f, you're finding y values. If you're plugging it into the first derivative, you're finding out if the graph is increasing or decreasing. If you plug it into the second derivative, what? Exactly. So it all just depends on what you're trying to find. In this case, they said find coordinates, so you plug it into the function. Alexis. Question? No? Watch something good? Fine. All right. Yes, Steve.
I did. Okay. Another question is, how do you plug in the negative side into that?
What I do is I typically do a parenthesis, and then I do -6 plus root 76, and then another parenthesis divided by 4. That gives me the entire expression when it's a plus. Then I hit second enter. I go back and then change it to a minus. That gives me the entire expression when it's a minus. So my two possibilities are 0.67 and 3.6. Okay. Sweet. Good. Okay. All right, folks, let's go ahead and take a look here at number 9. It's done by Sarai. Wait. Sarai, did you do number 9?
Yeah.
And I bet I just have to flick back here. There you go. So you did number 9. It's right here. Kind of tough to see because there's a graph right there, but just let's look at what Sarai did. So she knew she had a function, a 2x cubed, which a cubic looks something like that. And it says it has one local min and one local max. So there was her max, there was her min. And what are the coordinates? So Sarai took her function, she took the derivative, she set it equal to 0, divided out to 6, she had a quadratic, she factored it, she knew that 7 and 1 were the two values of the inflection, no, the critical values. So at 1, she had a max or a min, and at 7 and at 1, she had a max or a min. So now it's just a matter of finding the coordinates. So to find the coordinate, you plug it back into the function. So she plugged in 7, she plugged in 1, and she got these two values. Now at that point, it might be helpful to think of that as a coordinate. She had one coordinate of 7, -191, and another coordinate as 1, 25. And so that's how she knew that this one was up here, and this one was down here. And therefore, that has to be a maximum, and that has to be a minimum. So the final answer, folks, is a picture. That's what I'm ultimately looking for, is a picture of this right here, and that's perfect. Could Sarai have shown me a little bit more data, like that's 25 and that's -191? That'd be nice to see. But overall, you did the problem right. Okay, so that was number 9. Number 10, I think I do. And then okay, let me go ahead and do 10. I'll do it over, whoa, I almost just erased that work. Okay, number 10. I have a function with a minimum and a maximum. So this is just like Sarai's problem. I'm going to take my function, and I'll take the derivative, which is 7 minus 9x to the -2, which is 7 minus 9 over x squared. I'll set it equal to 0, and that gives me 7 equals 9 over x squared, which I write as a fraction, so I can cross multiply, and I get 7x squared equals 9, and I divide out the 7, and I square root both sides. So I have x equals plus or minus root 9/7, which I might as well get a decimal. Right, we want a decimal so that we know where to put all of this stuff. So the square root of 9/7 is plus or minus 1.13. All right, so now I can start making a picture of my graph. I have one at 1.13 and one at -1.13. And now the question is, where do I put those coordinates? So how do I find a coordinate? You just plug it into the original function. So if I take my 1.13 and plug it into that, to be very accurate, you'd want to use the original root 9/7. So I put in 7, plugging in root 9/7. and then plus 9 divided by root 9/7. That gives me up here a value at 15.87. And then if I plug it in negative, I get negative 15.87, which is down here. Now, folks, look at what I know so far. All I know so far is that this is a flat spot and that's a flat spot. And if you were just to take a guess, like, well, what does the whole graph look like? If that's a max and that's a min, you might make a bad guess and say, my graph looks like this. You know, that would just be taking a guess. And it's a bad guess because it's wrong. That's not what the graph actually looks like. You would need to graph this function to find out what it really looks like. What it really looks like is this. Oops, wait, there. That's what the graph really looks like. And so even once you do all the work of finding the coordinates of the maximum and the minimum, it's really helpful to just look at the graph on your calculator to know what it looks like. And now I know that I have the correct graph, where this is actually an asymptote in between those two values. Okay, well that was it. It said draw a picture, so there's my picture. Are you allowed to use your graphing calculator on the test? Of course you are. Every single problem you can graph. Okay, thank you very much. Now number 11 was Bata. So number 11, he has a function here, and it says, consider the function 5 minus 2x squared, which is just an upside down parabola. You can graph it yourself. And it says find the local min or max, and then the endpoints. So to find the min or max, you take the derivative, set it equal to 0, and he found the critical point at 0. And then when he plugged 0 into his function, he got the point 5, so that's the coordinate 0, 5. So he knew he had a point at 0, 5. But then the problem also says to find the endpoints. That is the endpoint of the interval from -4 to 2. So you just take those endpoint values, you plug it into the function, and you get those coordinates as well. So you have a coordinate -4, -27, and the coordinate 2, -3. And that's what he put right here and right here. And at that point, you just draw a line to connect the dots. Yep. Now, in the homework, they were asking the question, what's the absolute maximum? So what's the absolute maximum? This point. That's the absolute maximum. Where's the absolute minimum? This point. Where's the local maximum? Here. Where's the local minimum? There isn't one. There is no local minimum, because a local minimum looks like this, and a local max looks like that. So there is a local maximum on this graph, but there is no local minimum. There's only an absolute minimum, but no local minimum. Okay, questions about any of those? Alrighty, so next, number 12, is that where we are? So Allison and Michelle, come on up. Allison and Michelle. Thank you all so far, very nice solutions. There you go. What's up? Did you have another question? I did, okay. Now let's see. Simone didn't ask me a question yet.
About just weeks.
You started. What was it, your work? Was it down there? Oh yeah, that's it. I remember that. Yeah, I remember you sending me that. And the way you have it started, it looks like a revenue problem, but then you do revenue minus cost, and then it's profit problem. And when you first emailed it to me, I had no idea what the original problem was. All right, well, there it is. Yeah, so at this point, that's your formula for profits. So they want the marginal profit, which is the derivative. So you would take the derivative of that. And then you would set it equal to 0, and that would be your critical point. Oh, yeah, very good, you did. Oh, you got those using Desmos. Well, let's see. Oh, we didn't finish. Oh, you certainly can, because at this point, it's just a quadratic, so you use the quadratic formula. Yeah, yeah. Does that answer your question? Okay. I'm sorry? Yes. I need help, but it's only
Okay. So to find the max, what did you put the
right. So the first thing I did was find the local minimum, which you do by taking the derivative and setting it. 0. So when I took the first derivative, I got negative 4x, I set that equal to 0, and the only solution was 0. So x equals 0 gave me the local minimum or the max. And then I took the 0, plugged it back into the function, and that gave me my first coordinate. My coordinate was 0, 5. And that's the coordinate 0, 5. So that's my only local min or max. But then it said to find the endpoints. And the endpoint is a negative 4 and a 2. So I plugged in negative 4, got negative 27, that was that point right there. Then I plugged in 2, got negative 3, and that was that one right there. So at that point I had 3 coordinates, the local max and the 2 endpoints. You just draw them.
So what was the point of doing that?
The point of doing the second derivative, I took the second derivative, which the derivative of negative 4x is negative 4. No matter what value I plug in for x, it's always equal to negative 4, which is concave down. That tells me that the entire graph is concave down. The whole graph. Everywhere it's concave down, which you can tell from this graph is a concave up or concave down. Yeah, concave down.
Yeah, okay.
Yeah, so the second derivative is just telling me that since there's no x in it, the answer is always negative 4. What's the concavity here? Negative 4. Concavity here, negative 4. Concavity here, negative 4. Concavity is always negative, which means the whole graph is concave down. Okay. And that just told me what my graph should look like. Let's see, I think these two people already finished their 2 problems. So let's take a look. Number 12 was done by Allison, and number 12 was done right here. So it says, given the function below, approximate the intervals where it's concave up, concave down, and where's the inflection point? So Allison, I like what you did here. Allison put, definitely this is concave up, definitely this is concave down. This point looks to be in the middle of the 2, and it looks like 3 is a reasonable approximation of the inflection point. So she said the inflection point was 3, which therefore meant everything to the left of 3 was concave up, and everything to the right of 3 was concave down, and that's what she wrote down using interval notation. So very nice solution, Allison, that'll do it. All right, and then number 13 was Michelle. Michelle, that was the revenue, find the marginal revenue using both pre-calculus and calculus. And by the way, it was at 15, right? Did I not have that in the paper?
Yeah, I was gonna ask, where did you get that number from?
Did I email that to everybody? Yeah, I didn't give you a number to use, so that's a little confusing. Where did you get 15 from, Michelle? Always on the answer key. So apparently in the solution key, I just pulled out 15 out of the blue. On the test, I would actually say, find the marginal revenue at a particular value. I'm very sorry, folks. That's a little confusing. You need to be told a value to choose. And so that's what Michelle did. She did the revenue of 15 units minus the revenue of 14 units, which is going to give her the revenue at exactly the 15th unit. So she plugged 15 and 14 into that formula, and she got a difference of 55. So that is the actual exact revenue from the 15th unit sold. And then in the calculus method, you just take the derivative of your revenue formula, which is negative 10p plus 200. Again, plug in 15, and she got 50. That's an approximation. So both answers are very close, 55 and 50. One is exact, one is approximate. Okay, that was number 13. Now, folks, I only have 5 minutes left, and we have a few problems left. Is there one in particular you'd really like to see done, as opposed to any others? The last few questions are all about business applications, and then 19 and 20 are the elasticity. We just did elasticity today, so let's not do 19 or 20. Which ones would you like to see? 17, 18, 16, 15, or 14? Anyone have a special preference? Anyone want to choose one that you'd like to see? If no one has a preference, I'll choose one that I think is a good representative problem. Okay. Well then, let's go. Let's say we do number. Consider that one, find the inflection points. I'll try to talk about a couple of them. I'll do 14 and 18. So number 14, it says it has inflection points. That immediately means the second derivative. So the first derivative is 60x to the 4th plus 240x cubed minus 300x squared. And then the second derivative is 240x cubed plus 720x squared minus 600x. And then it says to find the inflection points. So that means take the second derivative, set it equal to 0, and then you can all factor out 60x, I think. So that leaves you with 4x squared plus 12x minus 10. Is that what you all got?
120.
What?
I just multiplied by 120.
Oh, okay. So now, I suppose 120, you're right. I can take out another 2. So now that's actually going to be 2x squared plus 6x minus 5.
Yeah.
So,
Sorry to cut you off. I was going to ask, so how did you go from 60 to 120?
because I realized I could take out another 2.
So you take out a 2 and then you times it to the front?
Yeah.
Okay, I didn't know that.
Oh yeah, you can totally do that. Okay, so now at this point, folks, this will equal 0 when x equals 0, and this will equal 0, and you have to use the quadratic formula. So again, to Simone's question, will I give you the quadratic formula on the test? Sure, I'll give you the quadratic formula. So the other solution would be -6 plus or minus the square root of 36 minus 4ac, so that's 76, all over 2a, and that would be your two solutions. You plug it into your calculator, and you'll get a decimal value. I'm not sure what those decimal values are. Actually, no, we just did that, didn't we, Stephen? It was 3 point something and
3.68 and 6.79, sorry. 0.679.
Okay, are they both negative?
The 3.68 is negative, the other one's positive.
Okay. So, folks, you do the second derivative, you set it equals 0. Now you have a number line with negative 3.68 and 0 and 0.679. And as before, you choose test values. So I would probably try -4, try -1, try 0.1, and then try 1. But notice here it's saying, oh yeah, determine if it's concave up or concave down. So you're going to do the second derivative at each of those values. And you just have to find out what the sign is. Is it positive or negative? And you just plug in -4, -1, 0.1, and 1. Okay, so that's just a sketch of that solution. I didn't finish it. Okay, I don't think we have a ton of time left. Let's skip to 18, just about to ask about it. So a company's revenue function is given, the cost function is given, and find profit. Okay, great question. So profit is always revenue minus cost. So you have to very carefully take the revenue and then subtract the cost. So I'm going to write that 16q plus 400. And you distribute the minus sign and you get negative q cubed plus 310q squared minus 16q minus 400. If that is your profit function, and then they say how many items need to be sold to maximize profit, that means take the derivative of profit. Negative 3q squared plus 620q minus 16, and set that equal to 0, and again, you'll use the quadratic formula. Okay, well, I realize I can't keep you any longer. I wish I could, but I can't. So it's 12:50. When you come back to class on Wednesday, bring everything with you. The practice test, your notes from chapter 2.5b, 2.6, 2.7, 2.8, 2.9, 2.10. Bring all that to turn in with you. If you have any questions between now and then, please, one, come to my office hours. I have office hours right now until 2 o'clock. Come along with me. We'll go to my office and we can work together. Or email me and I'll email you back. Keep in mind all of the more assignments you do on Wednesday as well, but you can use a late pass and extend the due dates of those more assignments. And that's it. Do what? The practice test? It's in more.
So you're supposed to
Oh no, you don't have to plug that into the computer. It's just on paper. Yeah, you just turn it in on paper.
I got a question for you about like play on words. So this is it has the collection of points. That means you can automatically find the second, right? Okay. And also probably just did 18. Yeah. So you said when it says something like the cost function, simplified profit function, maximize profit sold. Okay. Yeah. So that means you find the derivative of
The first derivative, yeah, and set it equals 0. Yeah, exactly the point. So Stephen, if you want to find maxes and mins or maximize, it's first derivative set equal to 0. If you want to find inflection points, it's second derivative set equal to 0.
Okay, so max, min,
First derivative. Yeah, very good.
Who's our